This video covers D3 zoom behavior. The structure of this video is as follows. The goal: D3 zoom behavior, D3 zoom X and Y scale, D3 scale and scale extent, D3 translate, D3 zoom event listener, example code explanation, JavaScript console walkthrough, and the summary. Alright, let's get started. The goal. Let's take a close look at what we are going to be building in this video. This webpage has the D3 library imported from the D3.js.org website. This video is going to investigate the D3 zoom behavior. This technique is useful in regular data visualizations, force layout diagrams, as well as in geographic visualizations. We will generate one SVG circle and an X and Y axis. In addition to the circle, we will define specific zoom behaviors that we can apply to the chart. The D3 zoom behavior allows for zooming in, zooming out, as well as panning the SVG elements around the SVG viewport. The behaviors you are seeing on the screen show different simple behaviors we will cover. This will show us the basics of what is possible with the D3 zoom behavior. D3 zoom behavior. This code constructs the zoom behavior. Both mouse events and touch events are supported by the zoom behavior. What this code does is create an event listener to handle the zoom gestures on the SVG elements we apply the zoom behavior to. In the case of zoom, this includes the mouse wheel zooming in and out, as well as the touch pinch and expand gestures for zooming. Additionally, the panning gestures of mouse down and moving, as well as touch and move, both work. For this video, we will assume that the mouse events are equivalent to touch events. Obviously, a mouse zoom is slightly different than a pinch/expand zoom. So for the purposes of understanding the basics of the D3 zoom behavior, we will only talk about mouse events for the rest of the video. For the basic examples we will be doing, you can think of them as equivalent. However, if you are implementing something more complicated, it's worth exploring whether the behavior you are coding up is equivalent in the mouse/touch space worlds. The D3 behavior zoom event is actually two different sets of behaviors that are interrelated. The zooming behavior is made up of being able to zoom in and zoom out. The panning behavior is made up of being able to pan along the X and Y axis. You can think of panning behavior as moving the camera across the image. That is, everything stays the same distance from everything else, it's just that the images all move together. The reason that zoom and pan are interrelated is that when you zoom in on a specific point, not only do you need to zoom in, you also need to move the camera so that the point you zoomed in on is still in the picture. This works the same way when you zoom out. When you zoom out, the amount of screen space that you are viewing changes, so the camera has to move as well. We will cover this more with JavaScript examples later in the video. Next, let's talk about the zooming in and out events. A few event types that we haven't covered before are the mouse double-click event and the events that cover a scrolling of the mouse wheel. As you can probably guess, the mouse double-click event is where the mouse is clicked twice in the same region at a speed fast enough to register as a double-click. As you can probably also guess, the mouse wheel events cover the scrolling of the mouse wheel. The mouse double-click event in the zoom behavior will be a zoom in. This functionality should be familiar to you from Google Maps or any other mapping software out there. This double-click also works with touch events. As you can imagine, and as we'll soon see, the double-click zoom is one-directional. Double-clicking only allows you to zoom in. It does not allow you to zoom out. The wheel type events in the zoom behavior provide zooming in and zooming out capabilities. This functionality should be familiar to you from Google Maps or any other mapping software out there. The mouse wheel event is abstracted from us in the D3 code so that we don't have to deal with browser-specific issues. We just have to know that the mouse wheel zoom is two-directional. Using the mouse wheel scroll, we can zoom in and we can zoom out. The one thing we want to pay attention to here is that users can set their own specifications for the number of lines a mouse wheel turn actually scrolls. So whereas a mouse double click is the same for everyone, the mouse wheel turn will differ from person to person depending on their setup. This is very important to remember because it means the experience of your data visualization could vary drastically across your audience. D3 Zoom X and Y scale. Let's talk about what a theoretical zoom event should be like. We double-click on a part of the graph. The graph should zoom into that point, and the graph should pan to the spot we double-clicked on so it is still in the view. Theoretically, that's how a zoom event should work. However, how can we visually tell it worked? What visual clues would lead us to believe that we have zoomed in or zoomed out? One way to tell is to figure out if objects in the chart change sizes. If a chart object increased in size, then we must have zoomed in. If a chart object decreased in size, then we must have zoomed out. However, visually, it is very hard to tell how much we have zoomed in or how much we have zoomed out if a change of size is all that we can see. The best way to figure out if we have zoomed in or out is to add axes to the graph. If we have zoomed in, then the scale of the axis shows a smaller distance than before from the largest number and the smallest number shown on the axis. If we have zoomed out, then the scale of the axis should show a larger distance than before from the largest number to the smallest number as shown on the axis. This is the D3 linear scale. Remember that the domain is the set of values that we start with and the range is the set of values we want to convert the domain to. For the most part, the range in the D3 visualizations we have created is just the height or width of the inner drawing space. Let's think through what our theoretical zoom would do to our scale. We start with the x-axis scale. We want to map the domain of 0 to 100 onto the range of 0 to the width. This makes sense, and we can easily create the D3 axis function and then call the function to create the visual x-axis elements. If we zoom in, what should change is the domain of the linear scale function. We are now mapping a smaller number line onto the range of numbers. This should make sense. If we zoomed in again, then we would have to make the domain even smaller. If we zoom out, what should change is the domain of the linear scale function. We are now mapping a larger number line onto the range of numbers. This should make sense. If we zoomed out again, then we would have to make the domain even larger. When we zoom in or out and we change the linear scale, this will have repercussions on the SVG axis function and how it is drawn on the screen. So when we redraw the chart after a zoom event is triggered, we will want to redefine the scale as well as call the SVG axis function again so that it redraws the axis on the screen. Luckily for us, D3 has the redefining of the domain for each x and y axis scale built into the zoom behavior. It will do the math for us and figure out what the new domain of each linear scale function should be given the zoom in or zoom out event that was captured. This saves us a few steps and makes the code much cleaner. Let's take a look now at what this looks like. This webpage has the D3 library imported from the D3.js.org website. We have recreated the example without the circle in the middle. This is so that we can concentrate on the x and y axis. Before we zoom in, pay close attention to the domain of the x-axis and the domain of the y-axis. Both go from 0 to 325. Now, I zoom in by double-clicking on the origin point. You can see that the x and y scale now go from 0 to 162.5. This is what we would expect to happen. And we did it by using the D3 zoom behavior x scale helper and the D3 zoom behavior y scale helper. We didn't have to calculate the math for the new domain. Next, I zoom out by using the mouse wheel. As I continue zooming out, you can see that the x and y scale go from 0 to 162.5 to bigger and bigger numbers. At the end, it looks like the axis goes from 0 to around 1650. Again, we didn't have to do the math. We were able to use the D3 zoom behavior x and y scale helpers. We have now covered how we can tell that we are zooming in and out using the axes. We have also covered how D3 can help us update them according to the zoom behavior by using the x and y scale helper methods that update the domain of the linear scaling functions. The next step in understanding the D3 zoom behavior is knowing how much we have zoomed in or zoomed out. D3 scale and scale extent. D3 provides a method to the zoom behavior that tells us exactly what zoom scale we are operating under. If we zoom in, then the zoom scale increases. You can think about it in terms of magnification. 2x magnification means that we have zoomed in so that objects are now twice as big as they were before, which we will be able to tell because of the x and y axis. If we zoom out, then the zoom scale decreases. This will be helpful later when we think about how to redraw SVG basic shapes. The default zoom for an SVG chart is 1. If we have not zoomed in or zoomed out, then the default zoom scale will be 1. This is something that I got wrong a few times when I started learning about D3 zoom behavior. The zoom scale can never be negative. The smallest number it can ever be is asymptotically close to 0. Why is this? The reason the zoom scale can't be negative is that it is a multiplicative process. We can think about zooming in terms of real-life distances. We can be twice as close or twice as far away from something, but we can never be a negative distance from something. It is the same way with the zoom scale. As we zoom out, the zoom scale will become a smaller and smaller fraction until it asymptotically approaches 0, which means that the zoom scale can be greater than 0 and less than infinity. However, JavaScript and the web browser experience strange behavior and break as you move closer and closer to 0 or infinity. This is because of how numbers are represented in JavaScript. One thing you want to focus on is making the data visualization useful to your users. Sometimes that means crafting the experience so that the visualization stays useful. Similar to the bounding box we covered in the D3 behavior drag video, sometimes it makes sense to limit what the user can do. In the case of the D3 zoom behavior, we can use the scale extent method to put a minimum and maximum bound on the zoom scale that the user can use. If it is not specified, then it defaults to a scale that can go from 0 to infinity, which will definitely lead to the visualization not being useful. Which comes back to the previous slide. It is very important to have a think about what types of zoom scales are useful for your visualization so that you can make sure to limit the scale extent to those. Let's take a look at some JavaScript examples to get a feel for how the zoom scale and zoom scale extent behave. This web page has the D3 library imported from the D3.js.org website. We have recreated the example without the circle in the middle. We have added HTML that will tell us the zoom scale we are currently at. Now, I zoom in by double-clicking on the origin point. You can see that the zoom scale is 2. Next, I am going to slowly continue to double-click on the origin point so that you can watch what happens when we don't limit the zoom scale. You can see that the zoom scale continues to grow and grow. Very early on into my double-clicking, the zoom stops being useful. Next, I'm going to use the mouse wheel to slowly zoom out on the origin point so that you can see what happens when we don't limit the zoom scale in the other direction. You can see that the zoom scale continues to shrink and shrink. Very early into my mouse wheel zoom out, the zoom stops being useful. In both cases, there are very few times when a user needs to zoom in more than tenfold in either direction. This is why it is important for you to think about what is useful behavior. I reset the web page and this time load up an example that has the zoom scale extent go from 1/2 to 16. Now when I try to zoom in, it will only allow me to zoom in until I hit the zoom scale value of 16. You can see that it stops me from zooming in anymore. Let's try to zoom out and see how far we can get. You can see that it stops me from zooming out anymore. This technique is very useful and makes visualizations have the correct boundaries to make them as useful as possible. When I zoomed in, the x and y coordinates of the chart moved slightly so that where I had zoomed in or out was still in the picture. We described this earlier as being the pan, basically the camera moving along the x and y axis. We cover that next. D3 translate. The panning behavior allows us to pan along the x and y axis. You can think of panning behavior as moving the camera across the image. That is, everything stays the same distance from everything else, it's just that the images move together. Rather than thinking about it like we are dragging one element around, think about it like we are dragging the whole coordinate space around. Everything remains in the exact location relative to everything else. It's just that the elements move around according to how it is being panned. We have access to the pan behavior regardless of whether we have zoomed in, zoomed out, or done nothing at all. This means that we can pan the coordinate system without doing any zooming. All we have to do is click down on an element and then drag it, and the whole coordinate system will pan with the mouse. The pan is done in the x, y coordinate SVG space. Horizontal is the x space, vertical is the y space. Let's take a look at an example on the screen. This web page has the D3 library imported from the D3.js.org website. We have recreated the example without the circle in the middle. We have added HTML that tells us the zoom scale we are currently at, as well as the pan x and pan y coordinate translations we are seeing. Let's start by clicking on the x-axis and moving it to the right. You can see that I panned the chart so that the 100 x-axis point is now at the far right end of the x-axis. The pan x translate tells us how many pixels we move to the right. We can move it back to the left as well. You can see that I panned the chart so that the 100 x-axis point is now at the far left end of the x-axis. The pan x translate tells us how many pixels we move to the left. In this case, we moved 100 pixels. We can also do this for the y-axis and move it towards the top of the computer screen. You can see that I panned the chart so that the 100 y-axis point is now at the top of the y-axis. The pan y translate tells us how many pixels we moved up. Did you notice that this is a negative number? This is because the SVG coordinate space is inverted along the y-axis. Let's move the y-axis back down. You can see that as we move it down, the pan y translate number gets bigger in the positive direction. We can also do a combo move where we move in both the x and y directions at the same time. You can see that the pan is able to update the x and y numbers at the same time. Lastly, let's zoom in by a factor of 2 by double-clicking and then try the pan. You can see that the pan is able to update the x and y numbers at the same time as we are zoomed in by a factor of 2. Note that the x and y translate still uses the number of pixels across the drawing space. So far we have covered zooming in and out, as well as being able to pan and what that means in x and y coordinate translations. The next step in understanding the D3 zoom behavior is to explore the actual zoom event and how it works. D3 Zoom Event Listener. Thus far we have covered how to construct a new zoom behavior that allows us to zoom and pan. What we have not covered is how to register the event listener that listens for a zoom event, as well as what is available to us within the listener function. The drag behavior has 3 different types of events that are supported: the drag start, drag, and drag end. Currently, the zoom behavior has only one type of event that is supported, the zoom event. This simplifies our life as we only have to write one function to listen to and react to this event. When the zoom event is fired, the listener function will be called. Within this function, D3 provides for us 2 different properties within the D3.event object. These properties are the ones we have been talking about. First is the zoom scale. Second is the translate vector. The translate vector is a vector because it has to carry information about the x coordinate translation and the y coordinate translation. The scale is the current zoom scale. If the zoom behavior was defined with a scale extent, then this will also be limited by the scale extent. This will be very useful when we go over how to resize elements when zooming in or out. The translate vector is a 2-element JavaScript array that represents the current x and y coordinate translations. The first element is the x coordinate, the second element is the y coordinate. Here within the event listener function is where the magic happens related to resizing the SVG objects when a zoom event occurs. For instance, let's think about a circle, rectangle, and ellipse. For a circle, when a zoom happens, we need to change the cx, the cy, and the radius attributes. For a rectangle, when a zoom happens, we need to change the x, y, width, and height attributes. For an ellipse, when a zoom happens, we need to change the cx, cy, rx, and ry attributes. This video will go over the thinking behind the resizing of a circle. From this, you should be able to figure out the resizing of other SVG basic shapes. Let's dig into the full example code for the explanation. Example code explanation. First, we define the height and width of the SVG container. We also define the data for the circle. We also define the D3 margin convention and use it to create the width and height for the inner drawing space. Next, we append the SVG viewport to the HTML body and define its width, height, and border. This will serve to give us a sense of where the SVG viewport is. Next, we define the X and Y D3 linear scales. The domains are set up so they go from 0 to the respective height or width. The range for the x-axis goes from 0 to the width of the inner drawing space. The range for the y-axis goes from the height of the inner drawing space to 0, as the y-axis in the SVG coordinate space is inverted. Next, we use the x and y linear scaling functions to define the D3 SVG axis functions. We give each axis an orientation as well as the number of ticks that we would like them to have. In both cases, we would like 5 ticks. Next, we define the zoom function zoom event listener function that gets executed when the zoom event is triggered. We are defining this now because we are going to run this section by section in the JavaScript console. If we were running it in one file or as a single contiguous block of code, we could count on JavaScript function hoisting. Since we are not doing that, this has to go near the top of the commands. The big picture overview of this function is that it figures out what scale we are on, as well as redraws the X and Y axis, as well as the circles. Let's go through it step by step. This is self-explanatory. We create a selection of all the circles inside of the SVG viewport. We will use this selection to update the attributes later in the function. This gets the pan vector, or as it's also called, the translate vector. As the translate vector is a 2-element array, we have to extract each element. The first element is the X translation, and the second element is the Y translation. These get assigned to separate variables because later we use them to write to the HTML elements what the zoom behavior is doing. This gets the zoom level we are in. Though we haven't yet defined the specific zoom behavior, if the zoom behavior has a scale extent defined, the definition will show up here as well. These lines of code select specific HTML elements and write to them text that specifies the current pan X, pan Y, and scale multiplier. Though this isn't always necessary for visualizations, I like to add this in order to keep track of data and to give a better sense of what is happening. We mentioned this earlier. The D3 zoom behavior allows us to designate the X scales and Y scales to the X and Y scale helper functions that help redefine the domain of each scale. In turn, these updated scales are available within the listener function. To redraw the scales, it is necessary to select all the SVG elements for each axis. Then we call the updated X and Y axis scales. This ensures that the visual X and Y axis will show the correct numbers on a zoom and pan. This is where the magic happens in regards to redrawing/updating the circle on a zoom event. Let's go over this line by line. The key thing to note here is that the zoom behavior has changed the x-axis scale domain for us. It has done the hard work with the math to figure out what the new x linear scale domain should be. So all that we have to do is pass the original CX data from the circle to the updated scale, and it will figure out what the right CX number should be. Why do we scale it? Imagine that we didn't zoom and just panned in the positive x direction. By panning in the positive x direction, it means we are moving the camera in the positive x direction, which means that our circle should be moving towards the negative x direction. If we move the camera to the right, everything in the picture should move to the left. This is where the new scale domain becomes important. The scale domain is the moving of the camera, and the number it returns once we pass in the CX should have moved it to the left. Note, this will work the exact same way if we have zoomed in or zoomed out. For the CX, we only care about the linear scaling function to make sure that the CX is correctly scaled in relation to the rest of the visualization. The key thing to note here is that the zoom behavior has changed the y-axis scale domain for us. It has done the hard work with the math to figure out what the new y linear scale domain should be. So all we have to do is pass the original CY data from the circle to the updated scale, and it will figure out what the right CY number should be. Why do we scale it? For the same reason as the CX. As we pan in the positive y direction, it means the camera is moving in the positive y direction, which in the SVG coordinate space means moving the camera down. As the camera moves down, everything in the frame should be moving up. So the scale domain is the moving of the camera, and the number it returns once we pass in the CY should have moved it towards the top of the page. Note, this will work the exact same way if we have zoomed in or zoomed out. For the CY, we only care about the linear scaling function to make sure the CY is correctly scaled in relation to the rest of the visualization. The key thing to think about here is how you would expect the radius of a circle to behave if we zoomed in or zoomed out. If we zoomed in, then you would expect the circle to become bigger. If we zoomed out, then you would expect the circle to become smaller. D3 gives us the current scale we are in. If we are zoomed in a scale of 2, then everything will look twice as big. If we are zoomed out a scale of 1/2, then everything will look twice as small. So for the circle, what we want to do is to multiply the radius by the zoom scale. As we zoom in, the zoom scale will get bigger, so the radius will get bigger. As we zoom out, the zoom scale will get smaller, so the radius will be smaller. Going back to the full scaling and panning of the circle, you can see that it will work regardless of what zoom level we are in. The zoom behavior function will recalculate the domain of the scaling functions for us and tell us the zoom scale, so we don't have to specify different scenarios for different levels of zooming. Going back to the rest of the code, this is where we define the D3 zoom behavior. We pass in the x-axis scale to the x-axis scale helper, which will redefine the x scale domain for us. We pass in the y-axis scale to the y-axis scale helper, which will redefine the y scale domain for us. We define the extent of the zoom scale to go from 0.2 to 10. Lastly, we define the event we want to listen for, which is the zoom event, as well as what function to call when the zoom event is triggered. The zoom function is the function we just got done defining and going over. Then we define the inner drawing space. This will hold the axes as well as the circle. The important thing to note here is that we call the zoom behavior on this SVG group element. This gives this element and its children elements the D3 zoom behavior. Next, we draw the x and y axes. The x-axis is translated the height of the inner drawing space to make sure it is at the bottom of the inner drawing space. Then we use the D3 pattern to create an SVG circle through the binding of data and using the enter selection. Note that before we even zoom, we are already using the scaling functions to properly place the CX and CY points of the circle. Lastly, we create HTML divs and spans to allow us to programmatically update the X and Y translations as well as the current zoom level. These are updated by the zoom function we defined earlier. And that is the last of the code. Let's now do the JavaScript console walkthrough. JavaScript console walkthrough. This web page has the D3 library imported from the D3.js.org website. We have opened the Chrome Developer Tools and are in the console section. We start by defining the variables used for the height and width of the SVG viewport as well as the D3 margins and the SVG circle. Next, we define the SVG viewport. Note that we added a border style to make it easier to see. In production environments, you do not want to apply a border to SVG elements as they are not supposed to render anything directly by themselves. That said, for this video, we use the border style to make sure we visually see what we have coded up. Next, we define the x-axis scale and y-axis scale. Note that we are using a 1-to-1 mapping for the x-axis. This is for ease of exposition. For the y-axis, it is an inverse 1-to-1 mapping because of the inverted SVG y-axis. Next, we define the D3 SVG axis functions. This should be familiar to you by now. We pass in the scale we want for the axis, choose an orientation, and then detail how many ticks we want on the axis. Next, because we are pasting code into the JavaScript console and cannot use JavaScript function hoisting, we define the D3 zoom behavior event listener function. This function selects the circles we are moving, figures out what translation has occurred from the d3.event.translate, as well as what zoom scale we are in. It writes these numbers to HTML so that we can understand what is happening. It then calls the x-axis and y-axis functions on the already drawn x and y visible axis elements to update them with newly updated scales. Remember, the D3 zoom behavior updates these scales for us. Lastly, we update the circle attributes to take into account the new scales for x and y coordinates as well as the zoom level for the circle radius. Now that we have defined the event listener function, we define the D3 zoom behavior function. Remember that the scale extent limits the zoom out and zoom in levels. With the D3 zoom behavior and event listener function defined, let's create the rest of the visualization. We create the inner drawing space. Remember that it is here that we give the SVG group element the D3 zoom behavior by calling the zoom function on it. Then we draw the X and Y axis on the screen. Then we create the SVG circle we will use to visually help us understand the zoom and pan behaviors. Lastly, we create the HTML div and span elements that will hold the key information regarding what the zoom behavior is doing as we zoom in and zoom out. First, we define the divs. You can see that we now have text labels for the pan X translate, pan Y translate, and the D3 zoom scale numbers. Then we define the spans as child elements of the HTML div elements. We use a span with a distinct ID to be able to programmatically change the text from inside of the zoom function. And there we go. We have now entered all of the code. Let's now play with the panning of the visualization to get a feel for how it works. As we press the mouse button down and pan the camera, you can see that the circle moves along the X and Y coordinates. You can also see that we can move the circle off of the screen. You can also see that we can move the circle on top of the axis elements. This is because the circle was the last thing drawn in SVG, so it will be the top thing in the visualization. Because we can use the zoom behavior on axis elements, you can see that we can lose the circle and then later bring it back by using the axis. Let's now play with the zooming of the visualization to get a feel for how it works. As we zoom in and out, you can see that the D3 zoom scale moves with us. As we zoom in, it grows all the way to 10. As we zoom out, it decreases until we are at 0.2. Also, notice that the panning still works at all the different types of zoom levels. And with that, we have covered the basics of thinking about, creating, and using the D3 zoom behavior. We covered how the translate pan works as well as how the zoom works. We created an example with a green circle to showcase what is possible at the most basic level. This technique will be useful in regular data visualizations, force layout diagrams, as well as in geographic visualizations. The summary. This video covered the goal of this video, D3 zoom behavior, D3 zoom X and Y scale, D3 scale and scale extent, D3 translate, D3 zoom event listener, example code explanation, JavaScript console walkthrough, and the summary.